Ironically, I just ran out of memory on my my hard drive there. Sorry about that. Anyway, there's plenty of room for improving the collision detection system. For example, having collisions able to happen on the z-axis, and therefore you can have the player maybe sliding down a surface, maybe have some basic physics simulation also applied there. I also want dynamic fluid simulation as well, because there's going to be memory kind of spurting out of enemies. So that's definitely something I want to implement as well, is physics and fluid simulation. What else? Weaponry. I mean, that's, there's not much to that. Currently just using. I'll start showing some code now, otherwise the video is going to be far too long. Go here. A bunch of structs and maps used for assets, and then determining the stats on a particular weapon using a class here actually. So these stat objects are then used to instantiate weapons on the fly using predetermined statistics for each of them. So yeah, there's the shotgun, there's the revolver. I mean, that's quite straightforward. Where's the weapon class? Yeah, you can just manipulate the mesh through using this interface here, render it to Vulkan, and then when you fire the weapon, it returns a flash effect and a vector of projectiles, which then the main game object can evaluate, update, etc. So yeah, here's the fire function. Yeah, it's worth noting as well that the camera for the character is not, I haven't done the usual trick of having a separate render pass where the weapon and hands are rendered on top of everything else as an overlay. The camera is actually locked directly to the player's head. So when I pitch over, the player's body pitches over. That doesn't look particularly good for his back, but yeah, I mean, literally all I'm doing there is just identifying where the waist is and then applying a transformation to any vertices above that point. So that's what's going on there. It leads to pretty interesting looking transformations. And there's a bug in, if you enable the flying debug camera, the player's orientation doesn't automatically swap to that. So that's what you're seeing there. Yeah, this is good to show you actually that the bullets do indeed come directly out of the barrel of the gun. So that's where the projectiles come from. So that's simulated sort of semi-accurately. Anyway, let's get to some more code because I'm running out of time here. Don't want to make this video too long. Core game mechanics and design, but over that. Enemies, talked about that. Future aims and features. I mean, there's a hell of a lot that I have planned. Obviously, this is very early stages. I'm just building out the fundamentals of the game engine before adding a lot more content. I think, to be honest, I don't really have too much time to talk about everything that I'm aiming for. But if you stay tuned, you'll see the game developing over time and the different features I'm adding in. If you have any suggestions for something you'd like to see as well, please feel free to leave a comment. Or if you have anything that you've seen implemented so far that you think could be improved or done differently, then let me know as well. Right, let's go over the Vulkan class. The Vulkan renderer class is a bit of a beast. Not a very pretty beast at that. I mean, this is the header file. The header file alone is what, nearly 800 lines of code. I mean, this thing is just, it's a bit of a mess. It's in desperate need of a refactor. So yeah, nearly 1,000 lines in the header, and the C++ file is significantly more of a mess. This is also in need of a refactor, despite the fact that I have another 2,000. I don't know how many. Lines of code is not a good metric anyway, but if you go off that, there's far too many in this Vulkan renderer. But yeah, it's set up in a pretty straightforward way. The basis for the renderer is based on the massive 200 and something page tutorial book by what are they called? The Kronos. It's a Kronos group. It's some offshoot of Kronos. I forget the name. Anyway, they've got a fantastic Vulkan guide. After about 200 and something pages of that, you'll learn to finally render a triangle onto the screen. So Vulkan is really low level. It's really verbose. It's very nice to use once you've got it all set up, because you can have very minute levels of control over pretty much every single thing that the GPU is doing, to the extent that people are even writing compute libraries for Vulkan, and those are performing really quite well, because it's so low level, and you can really access the maximum potential of the GPU using the API, which is great. Not so great if you're looking to create a simple game, unless you want to write a lot of code and populate a lot of structs. Here's some basic PBR materials I was using. These, I've got the numbers externally, so I probably will not use these in the final release, because I don't know if, maybe these particular numbers are copyrighted, but these ones down here, the ones I'm actually using for blood and gunmetal and stuff, I've created myself. Yeah, I don't really know. I mean, if I was to go over the whole of the Vulkan in implementation, it would take a very, very long time, so I'd best not do that. What else have we got here? I guess I could show some of the shaders. There's many shaders. I had to go making a compute shader. There's very basic, just particle simulation. So I have a compute kind of pipeline that can be used. I'm currently not using it for anything though. Here's the main shader for fragment shader for the environment. A lot of inputs here. Again, here's the different light positions that come in from the uniform buffer object. Here is a basic BRDF that's used for the PBR. That's based off Sasha Williams' implementation, although I've customized that a fair amount. Yeah, here's the different integers that correspond to the characters that can be rendered based on the level of grayscale. So as you can see, the grayscale float is created using this here, and then there's just a bunch of ternary operations to determine which one to actually use. Yeah, this is a bit of a mess. I don't know if it's helpful showing this, but anyway, environment manager. Here's the environment manager class. I'm using a unordered map with a custom key to store a vector of environmental objects that are within a given cube in three-dimensional space. So that allows for quite quick access. For example, for projectile collisions and other collision evaluation, you can just input the starting point and volume of the object that you're looking at, and then get back a vector of any environmental objects that are within that radius that you've specified, and then from there you can work with a far smaller vector than, say, 10,000 environmental objects. So that leads to a lot faster computations there, and means that in theory you get something close to O log n when you're computing things like environmental collisions. So that's useful. What else? What else might people find interesting? The AI, I suppose. Very straightforward at the moment. We're just following the player, evaluating if we're within melee attack range, and if we are, then attacking the player, pushing that back into a melee attack queue for this particular mob that the AI is controlling, and then those melee attacks can be evaluated for anything in theory. I mean, it just sends back a hitbox, which can be evaluated for the player. It could also be evaluated for other mobs as well. So that's that. Update uniform buffers. This is pretty straightforward. Here is how I'm doing. This mess down here is how I'm doing the instanced animation updating. As you can see, memcopy is used. Always get a bit nervous whenever memcopy is used, but there we go. There is a SSBO for each skin, for each base skinned mesh, and then we can push the matrix transformation data with an offset. We can copy that into the SSBO and then get that data in the shader. By inputting an offset. I've got to remember how I do this. Yeah, so you can put an offset into the specific renderable as it's being rendered, and then you can get only that specific joint matrix data for that one instance, and then using the unique alright, yeah, and then we have unique joint indices and joint weights for each vertex, for each instance of each skinned mesh. So that's how that works. It's a bit of a mess. This is actually a lot faster than I thought it was. I assumed that this was a major source of this was a major slowdown in my entire skin mesh system, was the fact that I was using SSBOs rather than dynamic UBOs. Dynamic UBOs can only have a maximum of 64 kilobytes inside of them. SSBOs are, I'm not sure what the limit is, but it's very high. But they're significantly slower. So I tried using UBOs, dynamic UBOs instead, and if you use dynamic UBOs, obviously if you've got to if you've got a lot of instances of skinned meshes running around, you may well have more than 64 kilobytes of individual matrix transformation data. And when that happens, you're going to have to create not only a system where you have individual dynamic UBOs, you have to have a dynamic number of dynamic uniform buffer objects, which is not trivial to implement. Anyway, I had a go at implementing it. I noticed almost no performance difference. That's not to say that there was none, but it's more that there are far more significant bottlenecks in the skin mesh system, which is basically the animation updating function, and the function that updates and interpolates the transformations. So that's what I'm looking at optimizing at the moment. Yeah, so that's that. What else might be worth looking at? Maybe the different projectile shaders. So you can actually use a push constant. I've got this vector here, and I've packed in the type of projectile as well as the dimensions into one vec4. So obviously you can then just evaluate the value of the x of that vec4. If it's equal to 1, then, you know, here's a default bullet, here's a default flash effect, here's a kind of bloody, you know, blood flash where it's red. So by doing this, you can create custom flashes or projectiles based on the type that the projectile is. You can then also use custom models for each projectile as well. Currently, the way I'm doing all the different stats and initialization of objects is I just have this nasty resources.h file, which is included in a lot of things, which therefore means that it has a significant impact on compile times when you change anything in here. So this is pretty crude. I'm starting to actually separate out the different structs and maps to, so for example, here's weapon res, and therefore that helps compile times quite a bit. I've gone significantly over time. This is probably going to be a two-part video here because this has ended up being very long. But thank you guys very much for watching. I hope this was interesting or informative, and if you have any questions or suggestions, or if you spotted anything heinously wrong in my code, please let me know. Much appreciate that. Oh yeah, here's the main gameplay loop, by the way. I probably should have shown this at the beginning. Very straightforward, very modular. This is just FPS monitoring, and everything else here just calls methods from the game object instance, and it just calls them in a certain order. That's literally it. This is the entire gameplay loop here. So there you go. Right, thanks very much for watching, and yeah, if you have any suggestions or comments, please let me know. Thanks very much.